The burning of anything is a chemical change. We call it combustion in chemistry. Combustion is the rapid chemical reaction of a substance with oxygen, and in parentheses I have the formula for oxygen, O2, that releases heat and light in the form of a flame. The chemical reaction for the combustion of methane, in parentheses is its chemical formula CH4, shows that new chemicals, CO2, known as carbon dioxide, and water, H2O, are formed. This is signified by this chemical equation up here, which is not balanced, but we see the chemicals that are reacting, CH4 gas plus O2 gas, go to or form, that's what this arrow means, carbon dioxide gas and water gas plus energy. We'll look more at chemical equations in Module 3, but I just wanted to introduce you to them so you would be more familiar with them when you saw them in Module 3. The formation of snow and ice is a physical change, and here are the two chemical reactions for the formation of ice. H2O liquid forms H2O solid, and snow is H2O gas going to H2O solid. We see on both sides of the equation the chemicals are the same, H2O and H2O. What is different is their phase. Gas on the left-hand side, solid on the right-hand side, and for ice, liquid on the left-hand side and solid on the right-hand side. So chemical reaction forms new chemicals, and a physical reaction does not form any new chemicals. Alkali metals are found in the first column of the periodic table, and in parentheses here I have the symbols for these elements. Capital L lowercase I is lithium, capital N lowercase a is sodium, capital K is potassium, capital R lowercase b is rubidium, capital C lowercase c s is cesium, capital F lowercase r is francium. Whether a letter is uppercase or lowercase is very, very important. So down here, physical reactions, this video shows the sublimation of carbon dioxide, which is carbon dioxide in the solid form going to carbon dioxide in the gaseous form. Again, we see this is a physical reaction because we have the same chemical, CO2, carbon dioxide, on the left and the right-hand side of the air. 19.3 grams per cubic centimeter. Those are the units here. Density units are mass per volume units. Here we have 65 degrees Celsius. This is the symbol we would use for that. And the boiling point of water is 100.0 degrees Celsius at normal atmospheric pressure, which is also known as sea level. The chemical formula for glucose, or blood sugar, is C6H12O6. So we look to these subscripts to the right of each elemental symbol. What this means, in a molecule of glucose, there are 6 carbon atoms, signified by the symbol for carbon. In parentheses, we have this capital letter C. So 6 carbon atoms. The 12 after the hydrogen means there are 12 hydrogen atoms, signified by the elemental symbol for hydrogen, which is capital H, and 6 oxygen atoms, symbolized by the capital letter O, which is the elemental symbol for oxygen. So for example, if 12.99 G is what we use to signify grams of capital N lowercase a, otherwise known as sodium, completely reacted with 35.43 grams of Cl2, otherwise known as chlorine, to form NaCl, or sodium chloride. How many grams of sodium chloride formed? We add the masses of sodium and chlorine to get 58.44 grams of sodium chloride. Now in chemistry, anytime we see this lowercase g after some numbers, that means grams. So the last digit is plus or minus 1 of its place value. So down here between 56.36 milliliter, that's what ml stands for, and 56.38 milliliters. Furthermore, you would know that the device used for the measurement had marking for the 10th of a milliliter, the 3 up here, but not the 100th place value. cm stands for centimeter, mm stands for millimeter, this Greek letter mu, m stands for micrometer, and km stands for kilometer. So here the MM stands for millimeter, G stands for gram, M stands for meter. So here we have this value with all these zeros. How would we say this? The correct mathematical name for this number would be 7 septillion 900 sextillion. But really what we're looking at is not so much how to name this, but how many zeros or how many place values are after that 7 and the 9. We take the decimal point that is not explicitly written, but is right there after those zeros, and we move it until there is only one non-zero digit to the left of the decimal point. And when we do that, we move it 24 place values. And down here, we would just say 0.0000. We would count all these zeros here and move this decimal point until there's only one non-zero digit to the left of that 2. And when we move that decimal point, we move it 23 times, which is what that exponent is. So up here, this would be 7.9 times 10 to the 24th, and down here, 2.99 times 10 to the negative 23rd. That negative means our original value is less than 1, and this positive exponent up here means that our value is going to be larger than 10, which it is, much larger than 10. So here, density is the amount of matter in a given volume, which is symbolized by the equation D, which stands for density, is equal to M, which stands for mass, divided by capital V, which stands for volume, or D equals M divided by V. In both cases, the slash and this division symbol mean the same thing. And as it states here, D signifies density, M signifies mass, and V signifies volume. The mass units in grams and the mass units are typically grams, and the units for volume are typically centimeter cubed or cubic centimeter. This is usually for solids, or ml, which stands for milliliter, which is usually used for liquids, but a centimeter cubed is the same as a milliliter, and L for liter, which is for gases. So remember that 1 centimeter cubed is equal to 1 milliliter. These two volume units are interchangeable. So down here we see how this equation can be rearranged using algebra, where mass is equal to density times volume, and volume is equal to mass divided by density. The relationship between Kelvin and Celsius is additive. Kelvin is equal to degrees Celsius plus 273.15. Fahrenheit and Celsius have different degrees and different points of zero. The freezing point of water is 0.0 degrees Celsius and 32 degrees Fahrenheit. The formula that relates Fahrenheit and Celsius takes into consideration the difference in 0 points as well as the difference in degrees. There are 180 Fahrenheit degrees for every 100 Celsius degrees. So 180 divided by 100 is 1.8 degrees Celsius. And let's see. So I see a problem in these notes. These equations were kind of put together, and that's not correct. 180 divided by 100 is 1.8. It needs to be separated. So let me write, and we see this factor in the equations that relate Celsius. What am I going to do? Okay, so I changed this, and we see this factor, 1.8, in the equations that relate Celsius and Fahrenheit. So here are the two equations. Degrees Celsius equals degrees Fahrenheit minus 32 divided by 1.8, and degrees Fahrenheit equals 1.8 multiplied by degrees Celsius plus 32. 90.0 degrees Celsius, 89.9 degrees Celsius, and 90.0 degrees Celsius. My data would be very precise, very close in value, but not very accurate, far from the accepted value of 100.0 degrees Celsius.